Hello everyone, welcome to Standard 11th, and this is the very first chapter of mathematics, which is sets. Now this word we often use in our day-to-day life. A set of this, set of that, so set of 10 pencils, set of 10 pens, then a set of letters in a word, in mathematically saying a set of numbers, set of different kinds of numbers in fact. So what does this actually mean, and how does set theory evolve? Okay, so these all things we are going to see in this chapter. So before we actually begin to study sets, we are going to see what is its need or application or idea behind the sets. So suppose this is a container, okay, and different things are here in this container, okay. So some things are here. Now there can be a ball, there can be a book, then there can be a pen or pencil. Okay, so how do we define what is inside this container? There are different kinds of objects, things. There is a ball, there is a book, there is a pencil. So you can say the things required by a schoolgoer. Okay, so we often play on ground, so there is a ball. We study, so there is a book. We write, so there is a pencil. But then this collection must be well defined. That means whatever we define this collection as, everyone should come under that category and nothing should be left outside of that collection. So this means the collection is well defined. So suppose I write this word, okay, you can consider this word mathematics. Okay, so what are the letters of this word? There is M, there is A, there is T, there is H, E. M is repeated, so you can repeat it or you don't. It is okay. So I am not going to write M one more time. Same with A. A has already been listed. Then there is T, which already has been listed. Then there comes I, there comes C, and there comes S. So we say that these are the letters of the word mathematics, right? Suppose you put these letters in this box. Okay, this is a box and there is M, there is A, there is T, H, E. Okay. So we say that such collection is well defined, and so we say that such collections only are called as sets. Suppose I say a collection of 10 best mathematicians all over the world. So can this collection be well defined? By well defined, we know what do we mean. That whoever is considered as best must come under this category. Otherwise, if not best, it should fall outside this collection. So this term best is very relative, right? So what I consider best, you might not consider it the same way, right? Also, there is no time period involved here. 10 mathematicians, 10 best mathematicians in the world, but in which era? Current, past, okay, past to which extent? Okay, we can even go back to Pythagoras, right, and Euclid. So nothing is mentioned here, the term is very relative, so such collection cannot be considered as a well defined collection, right? Because there is this ambiguity, whom to consider the best, right? So this is not a well defined collection, but this is collection of letters in the word mathematics. Right? So this is nothing but our set. So the definition of set is very simple in fact, but the need of it and applications are rather very interesting and important. So what is the need to build set theory? Why is the need to collect objects under certain category? Why do we need to distinguish one category from the other? So obviously a collection of objects with a school goer and collection of letters in the word mathematics are two separate categories. So what is the need to separate things? What is the need for this separation? The important application of it in current times is how to feed information in the machine, right? We all use different kinds of gadgets, devices, machines. There is smartphone, there is laptop, there is desktop. So much has been evolved. So we need data for it. We enter something and the machine gives us the required output. So this set, list in the listed form or in the table form is nothing but a logical mapping. So it is not that these tables and these lists are fed as it is in the machine. So machine doesn't understand a table, but it understands the logical mapping. Once you feed the information that collection of letters in the word mathematics, then the machine exactly knows how the word is spelled, mathematics, how it is spelled, and then what comes under it, what goes inside this box. Machine understands it. So it is something like an array. If you have read or known a little about computer programming, so the theories were developed and evolved long back in 16th and 17th centuries, but the applications are still relevant in current times. So the need is this, and that's why the set theory has been evolved, just to distinguish the collections of objects from one another, just so that we can conveniently give information to a machine and the machine can readily process it. So the definition is very simple. There are types, different types that sets can be built and sets can be represented. So before that, we are going to see how to identify whether an object or an item or a thing in fact is a member of a certain collection, a certain set. So there is membership relation that has been defined on a set. So now we know what is a set, a well-defined collection of objects, different objects. The sets are often denoted by capital letters. So this set, collection of letters from the word mathematics, can be denoted by the letter S. This collection of things a schoolgoer has can be denoted by, say, A. This is not a set, okay? So this will not be represented in the usual set notation. So for any set, the elements or objects lying in that set are denoted by small letters, small case letters. So the membership relation says that for a set A, suppose it has elements A, B, C, D, E. Okay, then you say that a certain letter is a member of that set if it actually lies inside the set, and you denote this membership by the Greek symbol epsilon. The symbol is epsilon, but it is in this context we are going to see that it defines the belongs to, the membership relation. So we say that A belongs to A. So for some set A, the big A, the small a is in fact a member of A. So there are various ways of saying the same thing. For example, we are saying A belongs to A in the symbolic form. This is in the word form. Then you can also say that A is a member of A, the big A. You can also say that A is an element of A. You can also say that A is an object in the set A. So member, element, object, belongs to, and this symbol all say the same thing, whether or not a particular element lies inside the given collection, the well-defined collection, or not. Similarly, you can say that B belongs to A, C belongs to A, D belongs to A, E belongs to A. Can I say F belongs to A? No. Since F does not lie in this collection, this is a false statement. So you just strike out the symbol, and in word form you say F does not belong to A. Similarly, you can also say that F is not a member of A. Also, you can say that F is not an element of A. So the same thing can be said in different ways. So this membership relation is very important. Also note that a set is represented here using curly bracket and commas. So the objects are listed inside the curly bracket and different elements are separated by commas in between them, right? So this is a very important fact, that if you are going to list out the elements for any set, you use curly bracket. Curly bracket says this is collection of all, and the commas separate different elements from it. So a member of any set is written only using its small case letter, and if I say something like this, then definitely a small case A and this A inside the curly bracket are two different things. So this is a member of A, where A is this set, but this A inside the curly brackets is not a member. You understand the difference? So only sets are written in curly brackets, members are written as it is, okay, as the small case letters are, okay. So this kind of representation is called as roster form. So roster form is nothing but listing out of elements inside the curly bracket, and members are separated by using commas. There is another way to represent a set known as set builder form. So here in the set builder form, instead of writing each member separately, some common property that is held by these all members is in fact written. So for example, here the members of the set are A, B, C, D, E, the first 5 English alphabets, right? First 5 letters from the English alphabet. In fact, they are all small case letters. So this is the description for this set. So this set A can also be written as, in words, set of all or set of first 5 small case letters from the English alphabet. So like in Marathi we have Varnamala, A, A, I, I, K, K, G, Gh. Similarly we have in English the English alphabet. So there is no plural to it. It is used as it is in the singular form. Similar thing can be this. Now same thing I am going to write in the curly brackets. What I am going to write is, so set of all x say such that x is, or let us give a suffix, xi is a small case English alphabet for this I equal to 1, 2, 3, 4, 5. So this also tells the same thing. Here the letters listed are A, B, C, D, E. We are saying these are first 5 small case letters from the English alphabet. This description is also saying the same thing. Xi is a small case English alphabet for I running from 1, 2, 3, 4, 5. So there are 5 elements in this set. It's clear, right? Let us consider one more example. Let's say there is a set B. Okay. In the roster form, I am going to list down the elements as simply first 5 natural numbers 1, 2, 3, 4, 5. The same thing in the set builder form we can write as collection of all x such that x belongs to the set of natural numbers. This is the notation for set of natural numbers, script n. So it is not a capital N only, it is a bit fancy way to write it. So script n is the notation to write set of all natural numbers. X belongs to n. Here also we can say that in fact there are xi's for I running from 1, 2, 3, 4, 5. You can also write the same thing in a different manner. Say it is a collection of y such that y is a real number? Again, this is a notation to denote the set of all real numbers, the compilation of natural numbers, integers, rationals as well as irrationals. So, y is any real number which is bigger than 0 and less than 6. Okay, so y should be natural, yeah, and you can say this. So y is bigger equal 1, so 1 can be included, but it is strictly less than 6, so it should stop at 5. So all these are different forms of representing a single set. Here also consider the membership relation. So we had set B as 1, 2, 3, 4, 5. So can I say 3 belongs to B? Yes, 3 is a member of B. Can I say 5 belongs to B? Yes, 5 is a member of B. Can I say 7 belongs to B? No, because 7 can't be listed here because this is a collection of just first 5 natural numbers. Suppose we write a set C, let's say, where C denotes set of all prime numbers less than 20. Okay, so this is the description that has been given to us. Set of all prime numbers less than 20. Now we can actually list out the elements. So the very first prime is the only even prime 2, and then other primes are all odd. So it is 3, 5, 7, 11, 13, 17 and 19. So this is it. These are all prime numbers less than 20. So this is indeed a well-defined collection because no other number can go inside this collection and vice versa. Okay, so this is our set. How many elements are there? How many prime numbers are there in fact less than 20? 3 plus 3, 6 and 2, 8. Okay, so can I say that 11 belongs to this set? Yes. Can I say 23 belongs to this set C? No. 23 is not a member because though it is prime, it is not less than 20, it is bigger than 20. Can I say that this is a member of the collection C? No. Remember, whenever you use curly brackets, this is a notation for a set and not for a member. So, a member can be simply 5, but this 5 inside the curly bracket cannot be a member of this set. Okay, so these are all preliminary things which we need to consider. So there is nothing much as a basic concept of set theory. What you need to understand is just when to call a set, what to call a set, then how to represent a set and how to identify members from a set. So we are quickly going to see some examples from the textbook where we are actually going to do it, that we are going to identify whether the given collections are sets or not, and also we are going to see whether a given element or object is actually a member of that set. Okay, so let's do it. Yes, so open textbook page number 4, exercise 1.1. You can also keep the book ready with you for your reference so that it will be easy to understand. So the question 1 says, which of the following are sets, and also justify your answer. So we also need to give reasons to our answer. Every time we give a solution, there should be a logic that is behind it. So every answer comes hand in hand with the reason for it. Okay, so question number 1. Which of the following are sets? The collection of all the months of a year beginning with the letter J. So the question says, this is sub question 1 from the question 1. The collection of all months of a year beginning with the letter J. Is this a well defined collection? Yes, because once we list down the elements from it, no one will fall outside that category. No one will be left. So let us call this collection as capital A, and we are going to list down the members of it. So the very first month which starts with J is January. Then comes June, and comes July, and we stop. So there are 3 members in this set: January, June and July. That's it. There are 12 months, out of which only 3 start with the letter J, and hence the collection is well defined. So yes, it is a set. What about sub question 2? The collection of 10 most talented writers of India. Again, this most talented writers in India, the term is very relative, right? So the ones which are my favorite authors, I am definitely going to say that they are 10 most talented writers. But then your favorites can be someone else. So again, you cannot decide whether the collection is well defined or not. There is ambiguity. So some may say there are some Marathi authors, some may say no, there are some English authors, some can say no, there are some great authors in Kannada also, and many other languages of India. So this is not a well defined collection, and hence it is not a set. Similar with question number 3, a team of 11 best cricket batsmen of the world. Again, ambiguity, the collection is not well defined, even the era is not specified. So when to consider this talented writers or best cricket batsmen, right? So you can go in past, you can consider current, everything is open. So it is not a well defined collection. Then comes the collection of all natural numbers less than 100. Now yes, this we can consider as a well defined set. Why? Because you can actually list down these elements. Collection of all natural numbers less than 100. So natural numbers start with 1 and go on with the exact gap of 1 till 99, because the description says that the members should all be less than 100. So yes, it is a set. Then the collection of all even integers. Collection of all even integers. Let me denote it by C. So how do you denote an even integer? What is the definition of a number being even? That it has to be divisible by 2. It ends with 0, 2, 4, 6 or 8. The units place digit is one of it. So this you can in fact write in the set builder form instead of writing it in the roster form, in the listed form. You can say that it is collection of all x such that x is an integer. Again, this is the notation to denote the set of integers, script z. So this is a plain z, capital Z, you just add a extra line to it. Well, why Z? Because in German, the word Zahlen is used to denote numbers. So, Zahlen is to count, and hence the root word Zahlen comes in this notation form. So, x is an integer, also x should be even. So, x is 2 times n, where n is also an integer. So, you can in fact club this. So, we can write this as collection of all integers x such that x is equal to 2n for all integers n. So, n can be 0, x can be then 0. So, yes, x is even. N is 1, we are multiplying it by 2, so x is 2 even. N is 3, 3 into 2 6, x is even. Similarly, n can be negative also. So, n can be say minus 5. So, 2 into minus 5 again gives you an even integer minus 10. So, this in fact gives you the collection of all even integers. Here it says first 11. No, there is no such condition. It is just collection of all even integers. So, yes, this is collection of all even integers. If you want a certain number of even integers, so let's say first 10 positive even integers. So, D should be set of all or set of first 10 positive even integers. So, since we want positive, we will not consider 0. It will be simply 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and that's it. You can also write this in the set builder form like this. So, collection of all integers x such that x is 2n, but now what is the extra condition? X is positive, so x belongs to z plus. This is again a notation to denote positive integers, z plus. The plain z includes negative integers and 0 also. Z plus excludes all of them and considers only the positive integers, which is nothing but natural numbers. So, all positive integers such that x is 2n, where n is equal to 1, 2, 3 up to 10. So, these first 10 positive integers give rise to this set. Okay. The collection of questions in this chapter. Yes, it is again a well-defined set, a well-defined collection. So, we cannot actually write down the members of this set, but yes, it is a set. And the lastly, collection of most dangerous animals of the world. Again, the term dangerous is very relative. I can find even a dog dangerous, but to some it may not be that dangerous. So, again, this collection is not well defined, and so that cannot be considered as a set. So, these were the preliminaries about set. Okay, what is the idea behind developing set theory, when it is developed actually, how it is useful and relevant even in the current times, what is the need of it, what is the application, what to call a set, how to represent it, and how to identify members of it. We have seen all these basic concepts in this session. In the next session, we are going to see some more examples based on this basic concept and also some more concepts related to the set theory and these sets. So, till then, bye.